elements of largest magnitude appearing along the diagonal where possible. And after that one, you solve for xi in the ith equation. And so once you solve, you rearrange, and then you now have the expression which is shown on the screen. That now becomes your Jacobi iteration scheme. And so you start with the initial condition, and then you start improving the condition until you converge. So if the solution, if your system is convergent, then as x approaches infinity, then you approach a solution. And so we stop given certain criterion or the tolerance. If the tolerance is met, then you stop your iteration. So today we want to look at the second one, which the second method called it's called the Gauss-Seidel. So this has to scroll up. So is Gauss, is it capital L or single L? You can check the correct spelling. So the Gauss-Seidel iteration scheme. So the Gauss-Seidel just starts in the same way as the Jacobi system. You rearrange your system or matrix such that you have diagonal elements appearing along the main diagonal where possible. And you solve for xi in the ith equation. So what happens that the Gauss-Seidel uses the latest updated value. So I will start just maybe writing. So assume we have already rearranged the system and solved for xi in the ith equation. As in the Jacobi method. So they just start basically with the Jacobi method. And first of all, recall that I told you that this J here is called the Jacobi iteration matrix. So if your matrix is diagonal dominant, then this method converges. If not, it may or may not converge. And so the sufficient condition to check that your method is convergent is finding the spectral radius of a matrix, what we mentioned last time. And the spectral radius is just the magnitude or the dominant eigenvalue in magnitude. So you find the radius eigenvalue in magnitude. That's what you check the eigenvalue. So if this is less than 1, then the scheme will converge. So at the end of this course, I will try to show you how to find the dominant eigenvalue for matrix, not necessarily without finding the whole eigenvalue. So you can just find the dominant eigenvalue by using the power method. And so who remembers? So I think we had like xy. I'm just illustrating this on this x3. So it is 0 minus a12 x2 over a11, right? Then minus a13 x3 over a11 plus b1 over a11. So I hope I'm writing the correct thing. Yeah, so I'm just picking out from where we solve for x1 and x2, x3. That x2 is the same. So this is okay. A21 over a22 x1, and then minus, this is negative, minus 0, and then minus a23 a22 x3 plus b2 over a22. And then I have here x3 is the same as negative a31 a33 x1 minus a22 over a33 x2, and then plus b3 over a33. So this is just basically what we did with the Jacobi. And he said, so starting from the initial condition. For example, that is x1 0, and then x2 0, and x3 0, and then we plug in. So we plug this into the first equation. When you plug this into the first equation, you'll have that now the first iteration of this equation is the same as 0 minus a12 over a11 x2 0, and then minus a13 over a11, no, yeah, a11 x3 0, and then plus b1 over a11. And so remember, once you solve for x1 in the first equation, you now have an updated value of x1. And so instead of using still the previous values in the to find x2, you use the new value which is present, the latest value. And that's now the difference between the Jacobi and the Gauss-Seidel. So it means now our x21 will be, that is a21 over a22. That's now x1. Remember x1, we have this new value already, which we got from the first one. And so I will use this x1. I'll have minus 0, and then minus this is 23 over a22, and then x3. x3 still, I don't have the latest value, so I still have just the initial value. This is a22, this is b2. And when you solve the x3, that is 1. This will give us what? I have already x1 latest, and then I have also x2 latest. Oh, there's something I was writing here as a22. It's supposed to be a32. Just to change this notation. It is a32, this last value. So that is a33 over x2 updated. Remember, so we now have x2 updated. And then this is minus 0, and then plus b3 over a33. Remember what I told you, that having those zeros is just for convenience, so that you can extract the lower and upper triangular matrices. But if you are solving, you can just get them if you are working out the system. So they are just there for convenience. And so what do you notice? It means if I go to the kth iteration, right, then I'll have, what do you notice? Let me try to do this and highlight. So if I draw this matrix, so which type of a matrix do I have on this other side? Which type of a matrix? Basically, you see that I can divide along the diagonal. I have the lower triangular matrix, and then I can split that one into an upper triangular matrix. So basically, an upper triangular matrix is taking the previous values, and then the lower triangular matrix is taking the coefficients of what? Of the latest values. So I can just write this maybe in matrix form and in more compact form as, so in compact form. That means here x2, no, this, let me just first write x1 is L, and then x1, and then this is plus u into x0, and then plus this is b, vector b. Let me just call this vector c, right? You remember, for example, like this, where L, what is L? L is just the lower triangular matrix with diagonal elements being 0. So that's 0. Everything here is zeros. And then this is A 21 over 2A22. That is A31 over A33. And then I have 0. This is 0. And then A32 over A33. Huh? No, there's something missing somewhere, right? No. Yeah, I think you are okay. And then this is 0. I have 0. I have 0. It's just a lower triangular matrix, and all these matrices, and then you can take U the same way. So your U is basically here, this is 0. That is A12 over A11. That's A13 over A11. And then I have here, that is 0. That is 0. That is A23 over A22. And 0, 0, 0. So if you have a large matrix, you can just continue the same way. Then you write the big L and big U. So first of all, is this okay? I've just taken this and then I split this into 2 parts. I'm just trying to skip some steps. So if you continue this way, so continuing this way, we get, what do we get? So we get that basically x into k plus 1 is the same as L into xk plus 1 plus U into xk and then plus C. So remember that C is the same as B over AII. And this is the Gauss-Seidel iteration scheme. So this yellow highlight. So this is the Gauss-Seidel iteration scheme. So it's, instead of having the matrix J, it splits. So once you can get that J, it splits the J into L and U. So you can start just from the Jacobi, you get the J, and then you split the J into an upper triangular and lower triangular matrix. And so lower triangular matrix takes the coefficient of the latest values, and the upper triangular takes the previous values. This okay? Any question? So I can, first of all, maybe get the Gauss-Seidel iteration matrix, and after then we can just illustrate the previous example with this scheme. So remember, I told you that for the Gauss-Seidel iteration matrix, for the Gauss-Seidel, the iteration matrix is just directly the J. This coefficient matrix is just the J, Gauss-Seidel. So when somebody asks you to find the iteration matrix for the Gauss-Seidel, you just simply need to write this, get the J, and then that J becomes the Jacobi iteration matrix. For the Gauss-Seidel, we need first of all to solve for xk plus 1. So remember, for the Gauss-Seidel here, I can take this to the other side so that I have xi, I can put here I, right? And then minus L x plus 1, that is x plus 1, is the same as U xk, and then plus, oh no, this is x plus C, right? And so after doing this, it means I can have here 1 minus L and then into x k plus 1 is the same as U into xk and then plus C. So since you have an identity matrix, this is diagonal, then this cannot be singular. And so it means I can find inverse both sides, and then I can have that xk plus 1 is the same as I minus L inverse U xk, and then plus I minus L inverse multiplied by C. And so this is this one misbehaving. So this guy here is called the Gauss-Seidel iteration matrix. So remember that to get the Gauss-Seidel iteration matrix, it requires some calculations. So I can just say maybe matrix the Gauss-Seidel is the same as I minus L, and then inverse multiplied by U. And so this is now where the other methods come in handy. So the method we learned about the Gauss-Jordan iteration, the Gauss-Jordan method, where you get this. But this matrix, I think it may have so many zeros or what it kind of have. It might, yeah, because you have all identity which has zeros only at the diagonal, and then you have. So this matrix, I think, to inverse will be easier because one side will have zeros. So it's kind of quick. You only need maybe like 1 or 2 steps to get to apply the Gauss-Jordan elimination method. You just need only a few steps because already some of them are eliminated already. They are zeros. And so this gives you the Gauss-Seidel iteration matrix. So it's different from the Jacobi is just direct. The Gauss-Seidel, you need to get J and then extract into L, split J into 2 parts, L and U. And after you split into 2 parts, L and U, and then you take I minus, oh, this is not 1, this is, so don't confuse. This is I, identity matrix. So it is I minus L and then inverse. So this gives us the Jacobi, the Gauss-Seidel. And just also, as we have said, that these methods converge if their spectral radius is 1. So if the other thing, but if you get that the matrix is diagonally dominant, then that one will always be satisfied. So if not, then you can check for this condition. So any question? Can somebody try to explain? Can somebody help? Can somebody explain where I came from? Anybody who remembers where I came from? Or who knows where I came from? Yeah, I is identity matrix. So he's asking, where did we get the identity matrix from? That's the question he's asking. Or why did we put identity matrix? Any trial? First, maybe before you explain it to me first, this is just a rough work. So you remember, because I'm just doing this because we look at eigenvalues. Eigenvalue say that a number lambda is an eigenvalue if this is satisfied, right? I hope you still remember this, right? Then if this is satisfied, lambda is an eigenvalue, x is an eigenvector. That's the definition. But this can be written as what? As ax minus lambda I x, right? Is the same as 0. So is this okay? The one who asked, is it okay? So, but you covered eigenvalues and eigenvectors, right? No, forget about this. Do you know where this I why I put this I here? This other I in the eigenvalues. Anybody who can help? If I want to subtract a number from a matrix, that's a matrix. That the other is a scalar, or this one is a vector. And so I cannot subtract a number, a matrix, and a scalar. I need to make the other also a matrix. And by making it a matrix, just by multiplying that by the identity. Because identity is what? It's a unit. So if you multiply, it keeps the same thing. So it's just like if you don't know how matrices, it's just like taking a number, then you multiply 1 by x. So that's what I'm doing. So I'm just multiplying by identity matrix because I need to subtract matrices. So I multiply the other part by an identity matrix of the same order with the matrix. Does that answer the question? Yeah. Yeah. So if you want to subtract a number from a matrix, then you have to, that's why you see when it's here, I don't need to introduce because I'm not subtracting. But whenever I want to subtract, then I have to introduce an I. And I just being identity, just multiply. The same thing happens with the eigenvalues. If you want to introduce, subtract them, then you need to multiply by I so that you make this a matrix. And so maybe we can look at the previous example, and then I look at the dominant eigenvalue, and then we illustrate the dominant eigenvalue by these methods here, by the same methods. So I'm just picking out from this example. So I hope you have this matrix. You'll remind us this matrix, right? Just remind me this matrix. So example, let me put here the Jacobian, meaning I'm looking at the same example we worked with Jacobian. So if you want, we will not finish it. We will just do only 1 or 2 steps of this method and then I stop. But so the Jacobian, this Gauss-Seidel method converges almost as twice as fast as the Jacobian method. And so if you want to test, if you want to know, take both methods, do the same example and see, just set a tolerance, for example, maybe 10 to the power minus 5 or 4 decimal places, and see which one achieves it very fast or quickly. You'll see that the Gauss-Seidel arrives there almost twice as fast as the other method. So the other one we had xk plus 1. No, let me just say x is the same as j x plus c, right? What is the j? Give me the j that in the other one, the previous example. Go down 6 over 15, and then negative 1 over 54. And then this other one, 27, 0, 54, 1 over 27, negative 2 over 15, and then 0, right? And then what is the C? The C is we did it.
85 over 27.
85 over 27.
It's over 27. Next.
72 over 15.
72.
And then next.
110 over 54.
110 or 54. Okay. So you know that. So these methods just start in the same way. So the difference is that now the Gauss. So I'm now writing here. Just I'm taking the Gauss idea from the Jacobi method, and then I can say let me write these equations as splitted. But if you want, you can just put what you can also put in terms of L and X. Do this whichever we want. You multiply. So this is xk plus 1 is the same as this will be 0 minus 6 over 27 x2, right? K, and then minus 1 over 27 x3 k plus 85 over 27. And then x2 k plus 1 will be the same as what? That's negative 6 over 15. Remember, so when you have this matrix, just split it. So anything, and this one taking time to highlight, anything below will take the latest values. So that's the L. So whatever is the L. And so then this is what? That is x1, k plus 1. And then minus, that is 0, minus 2 over 15, x3, and then k plus 72 over 15. Feel free to write this in matrix form so that you have just L multiplied by x, and then you'll be multiplying. x3 k plus 1 is the same as negative 1 over 54. That is x1 k plus 1, and then minus 1 over 54 x2 k plus 1 plus 0, and then plus 110 over 54. And then as I said, so let us just start with the same initial values. x1 is equal to 0, x2 is equal to 0, and then x is equal to 0. So as we did in the other one, I just also go directly to forming a table. So that working with a table is easier. So I have k, that's 0, 1, 2, it will do as, and then I have x1 k. I can directly go to k plus 1, and then this is x2 k plus 1. You can, if you want, you can put errors alongside. So x1 and then error x1, x2 and then its error x3 and then its error, and the same and so on. That is x3 k plus 1, and then you can just have their errors. Let me just write here maximum error, because if all of them, if you need your answer to 3 decimal places with the significant figures, all of these variables should satisfy that error. That means if I'm putting here the maximum error, it means I've taken care of what? Everything here. But I said, if you want, just have along each column, you are having the error as you go on. But again, having the error is not compulsory. If you can compute error and then you have them saved somewhere, you are just checking them somewhere. If they're satisfied, it's okay. So we start. If x is equal to 0, what is x1? Can somebody tell us if x is equal to 0? No. Yeah, if k is equal to 0, what is x1? Remember here, we're just still using the previous values. So I just have kk. That gives us 85 over 27, just the same as we got in the Gauss-Seidel. And remember, I think these tables are written them in different way, which is still okay. If you recall the table I wrote here. Here I wrote xk, meaning for each k I put the values. I can still just keep the k and here write the updated values. So it's still okay. The same way, whatever you want to make these tables, if you want to move them with the case or write the next values, is still okay. So if I put here xk plus 1, then I will not have these zeros. I will only have this. So this will move to the first row. So if you want xk plus 1, remember x2, xk plus 1, I am using the latest x1, which is 8/27, and then I use the previous xk. So can somebody give me this value? This is just plugging in your calculator. I told you, numerical mostly is kind of direct. What it needs is your practice and the speed. Because here, like if you understand this, so the rest is just what? Punching in your calculator, and then you put the answers. You punch and then you put the answers. And then you can even have your calculator just recording the previous values. You just keep on changing the values, and then you key in as you go. I know you guys must be an expert in this kind of things. So this should be quick. So what is x2? K plus 1. But I should not press you and then you give me, you are late. When I press you, at least you should. Msiniaibishe.
(478/135).
Put in the decimal. I just put this because I don't have a calculator. Can you put in the decimal?
3.54.
3.54. But so just we are writing the two decimal places if they're continuing. And I said, for example, if you want your answer to be satisfied to m significant figures or m decimal places or m whichever you want to work with, then you should work with at least m plus 1. So take note of this. If you want your answer to be accurate to 2 decimal places, it means you should work to 3 or more. If you want 2 significant figures, you should work to 3 or more significant figures. But for now, I just write what you said. The other one, remember, if we go to x3, we are now using the new x1 and new x2, and we get x3. So what is the third x? So as you do it, I'm eating grapes. Mwenye anatangulia anakuja nampatia. Mwenye anamaliza wa kwanza. Do you people have calculators? Hata naweza tumia simu na natangulia. What is it? So I think maybe this one I can leave it, then you will do it on your own.
1.913.
Is 1.913.
91.
I don't know if they are correct. I'm just writing whatever they give me. So I don't know if they are correct. So if they are wrong, you guys have to verify. And then so the error is just the difference between the current value and the previous value. So for each error, that's what we'll be doing. And then you check, is this difference accurate to what I want? Right? Any other question? No, next. Now, can you, when k is equal to 1, can you give me x1? Can you give me these values quickly? If, for example, now you move to k is equal to 1, it means you take these values and use in the first equation to get new x1. Can you give me those values? Have you gotten those values? And then even so, this method, you can also quickly and easily program it, or just like you call what we did in the previous method. So this one you can also quickly do the same thing, and you get the, because you are just only, instead of taking the previous values, you are taking only the latest value which is available. That's what you do when you make your program. Just take the latest available value, and that will be okay, and then it will be, you will have your solutions. So basically what we have looked at are just the iterative schemes for solving systems of linear equations, and they are just generalized methods for solving systems of linear equations. Just in particular, there are so many conjugate gradient methods and so on, like SOR methods. So I told you just that you should look at SOR method as an assignment. So it's an SOR method, and then you write the program alongside. Also write the programs that can find the roots, or the can solve linear equations using all these methods: the Jacobi, the Gauss-Seidel, and then the SOR method. And so that SOR method, you also just write down the formula, and then you also program it. In fact, it will just introduce you that whatever happens, we are just splitting the J, and how we split the J is what differs. So SOR method just gives some theta, is just called the theta scheme. So you multiply by some factors, the L and U, that gives you the SOR scheme. So once you understand these two methods, then you should have an idea, and then you should, in the future, depending on what you do, you should be able to work with any iterative scheme you meet. So in our class, just to introduce to you what is expected and what you need to do. And then also for these methods, and for this might be for your own revision, that these methods, you should go on to find their matrices, their corresponding matrices. Like you find now the Jacobi iteration matrix, you find the Gauss-Seidel. So I know that with the Jacobi, it's kind of direct. You just get the J, and that gives you the iteration matrix. For the Gauss-Seidel, you need to find now L. You take I minus L, you find the inverse, and then you multiply. So it's also direct, but let me say it's kind of needs a bit of some work, where you have to take I and then you have to inverse, and then finding the inverse, you can easily use the Gauss-Jordan elimination method. That's where now these methods now come in. So, are there any questions? Any question?
Excuse me, sir.
Yeah.
Can you take me to the three equations that we had? The one having the three unknown, the x1 raised to power k plus 1. I have a question there.
On what we already formed the system, or which one?
Yeah, just for the Gauss-Seidel after, yeah. Scroll down a bit, just down a bit, where we have the subscript k plus 1.
Here.
No.
More down.
Yeah, a little bit.
Yeah.
Just move.
Here?
Okay, even there. Yeah, I can see that we have this equation where the unknown x is actually iterating in the rate of k plus 1. So I have a question. What if we start iterating from k, not from k plus 1?
What do you mean with setting from k, not k plus 1?
So that if maybe we have x1, maybe we move x1 of k, and then so that the next value x2 will not now move to k, but it will move to k minus 1.
I don't understand.
Okay.
Just
What about,
tell me what I read maybe.
okay, move to that expression x1 of k plus 1. I got maybe that
This one.
the part that the part that had x1 of k plus 1. It was just there. I think you'll understand me there. No, move down.
Here.
Yeah. Okay.
Okay.
So here, look at the first expression. We had x1 into k plus 1 is equals to 0. And then we had 6 over 27 into x2 of k. So my question is, what if this x1, it moves from k and not k plus 1, so that x2 actually decreases by, it becomes k minus 1? Will that still work for Gauss-Seidel?
No, yeah, it's no, those are just dumb indices. I can let my k plus 1 be equal to k. And so it means, or if this confuses you, then I let k plus 1 is equal to m, right? That means where there is k, I replace by m minus 1. And so I'll put here m, I'll put here m minus 1, I'll put here m minus 1, right? But they are dumb indices. So this basically will be k plus k minus 1, k minus 1, this will be k. Is that what you are asking?
Yes.
Yeah, so they are dumb indices, provided, so because depending on the system you program, some of this system start from indexing from 0. So you can even put, if you put minus 1, it's still okay. And then it starts counting from 1. Provided there's a difference between this is 1 higher than whatever is here. Even if I put here k plus 2 and I put here k plus 1, k plus 1 is still okay. And the same thing happens in all the equations. And remember, if you want to deal with this system, you can still deal with it in matrix form, the way I wrote here. You can compute I minus L inverse U xk, but which is, so you are having a lot of time doing this thing here. But if you are like programming, you can quickly write this in matrix form, where you have this matrix where the system can easily find for you the inverse of this system. So let us just spectral radius. So as we said, so the Gauss-Seidel and Jacobi methods converge if and only if their corresponding matrices are such that, so rho is the spectral radius, so it's symbolized to rho. So for example, rho of J has to be less than 1 for the Jacobi. J is Jacobi. And then rho of the Gauss-Seidel, this is just the symbol, also should be less than 1. And then I said, so basically, rho of a matrix A is the magnitude of the dominant eigenvalue. So it basically checks even the signs. So you don't care about, you are just looking at the dominant, those eigenvalues, the values of the eigenvalues, the magnitude of the eigenvalues. And so the dominant one becomes the spectral radius. It's just like you can draw a circle that becomes the radius, and it means all the other eigenvalues lie within that radius or that circle. And so there are so many ways, you know, the ways of finding the eigenvalues. There are so many ways of finding the dominant eigenvalue. Of particular, we can look at this method. To find row A, we can use the power method. You just take an initial guess of the eigenvector and you start computing the matrix. You form those eigenvectors and then you normalize on one variable until they are the same. So this is the method I'm using, the power method. So recall what I wrote there, that if lambda is an eigenvalue, then this has to be satisfied, where this is the eigenvalue and x here is the eigenvector. So I hope you still remember how to find eigenvalues and eigenvectors. So here, this method, I'm not going to find all of them, because if I want to find it, if they converge, then we just only find the eigenvalues for the dominant magnitude or the largest eigenvalue, which is enough. And so the power method starts with the initial guess. So power method start with an initial guess. Say x, where can I put this? 0. Hello? Yeah? Ah, no, I forgot. Maybe let me try to check after class. I'm in class. Did you?
No, I'm trying to. I've seen the deadline is already passed, but the list too open. The system is too open. So once we check in,
no, maybe it's supposed to be 10 to 13, right? Maybe we can try to arrive. No, can you book for 2 people? That's the first question. Let me ask that way.
No, I cannot. For you book on your own.
Maybe send me the link, but maybe we can try to go there on 8. At least, maybe it's 1 hour, or we can just go there on 9th in the morning, so it's still okay, and then leave on 14 or 15.
So we say 9, right?
Yeah.
9 June.
So are you serving the hotel or which one?
That's a Sunday. That's
Yeah. It's a Sunday, so you can go there on Sunday.
It's Hilton. Hilton.
Yeah.
Check out.
Please send me the link. I'll check after class. I mean, because maybe I'm finishing in the next 30 minutes.
Okay, so check out that would be what we are to pay. It need to be 14, right?
But you have classes, so with you, maybe you need to come back quickly. So you can just come the day after. Yeah. That will be on 14.
So it's 14, okay,
yeah.
Okay, thanks. Okay, I'll send you the link.
Okay, or maybe okay, so it's okay. 9 to 14 is okay.
Okay.
Yeah.
Okay.
Yeah.
All right. That's okay.
Okay.
All right. Okay, thank you.
Hello. Sorry, I'm back. So I said that the power method start with an initial guess, say x naught, and then compute x1. No, I'm putting the power here such that. So you remember that. So I'm just trying to achieve this. So when you start with an x naught, then you say x1 is the same as a multiplied by x naught, right? And or let me call this y. Let me first of all not call this x1 and call it y. I wanted to combine the two things, but let me just do. Why is this thing and it takes time to delete what I need to delete? No, are you guys still there? Because when I don't hear people speaking, then I become worried.
Yes, we are here.
Naweza kuwa naongea na watu wameenda kutembea. But why is this now misbehaving? Delete. So what I wanted to do is, I wanted to do this so that first of all, you get vector y, then normalize y in the same way x0 was normalized. For example, when you set x0, what I mean is what? Maybe if it's a vector by 3, you can assume you're normalizing with the first variable. So it means you keep this one always. So in all these subsequent iterations, you are keeping the same variable you're normalizing as 1. Or you fix it. So it means whichever value you get here, you are now you divide by the quantity such that this value is always 1, 1, 1. So that means I'll have that such y is the same as what? I'll have this is lambda 1 and then k1. So when I say that this lambda 1 is a normalized vector, the same way x0 was normalized. And if this is an eigenvalue, if you arrive at an eigenvalue, then you get that these two things will be the same. And then continuing this way, you now also take now that, although this is just, let me say why this is y1. Then I can also say that y2 is the same as what? Now this is a x, and then this is 2. And then after you do this y2, and then you also normalize this, that y2 is the same as lambda 2, and then x2. So you keep on generating this sequence of vectors as you go on and you normalize until it will converge. And so if it converges, so if you continue this way, then you get that this is xk, this is k. So this coefficient after normalization will be the dominant eigenvalue. And then this will be the corresponding eigenvector. So it's called the So any question? So it means you can go back to all the other methods and then you try to find their spectral radius, all the Jacobi method and all the other method. I don't know if I can quickly find the eigenvalues here. And so, because so this assumes that the eigenvalue is not, I think, repeated. But so let me first pick just an example here. Then we can explain with an example. Then example, find row A where A is given by what? Is 2, 0, 0, 1, 1, 2, and then 1, negative 4, and then 1, negative 1, 4. Hopefully it works. So I said that to find the eigenvalue, you find the eigenvector. So see here, since you know that these are 3 by 3, the eigenvector will be composed of 3 components: u1, u2, and u3. So choose whichever eigenvector you want, choose whichever value you want, provided you normalize each variable you want. You can normalize the first one, normalize the second, or normalize the third one. So whichever you normalize, when you form this guesswork vector, that quantity is fixed to 1. You fix it to 1. So can somebody give us our starting x naught? Just the guess, and then tell us the variable we want us to normalize. And so if you are doing in an exam, don't copy your friend because you saw your friend now having 1, 1, and then you think you are, all of you, whichever normalize, you will arrive at the same answer. So can somebody give us the matrix to start with? Somebody tell me the vector I start with is just any vector. You are guessing any vector I start with. Yes? You said 1, 2, 1. So which one are you normalizing here? Just pick any value among those things, and then you tell me that we normalize this one. Note so when I mean normalize, it means if I decide to go with x3, and I set it like here, you set it to be 1, it means in all my subsequent vectors I'm generating, I'll always be keeping that value 1. So whichever value I obtain, assuming I multiply and I get maybe another vector like 10, 15, 20, and I was normalizing x3, it means I have to divide by 20 so that this is 1. So this can be written as what? As 20 into, that's 10 over 20, 15 over 20, and then 1. That's what I mean by normalize. So you factor out the coefficient such that that quantity you are looking at, or that variable, is fixed to 1. That's the easiest way. You can fix to 10, but instead of dividing, finding that how I need to make this 10 is confusing. So the easiest way, just make it to 1, whatever you want to normalize. And so it's your choice. You can normalize whichever you want, and I told you that each one will work. So which one do you want?
We can normalize the first one.
Okay, so the first one. So it means in all our calculations, we will make sure that the first variable is kept to 1. But again, if you are guessing some of these things, just start simple. If you want to just keep this as 0, start with 1, 0, 0. But I'm going to use what you have. I'm just saying that what we need is simplify calculations. So by putting here 0, 0, at least you know that the first multiplication will be simple. But so now, so I can say that now y1, or let me say, what is a x naught? Just tell me this quickly. So you are multiplying the matrix A by this vector, and this you will just, even if you are you will program this. As you program this, remember A will always be fixed. What will be changing is what? X1, and then normalize. So multiply. If you multiply these vectors, what do you get? You are multiplying A multiplied by this. I hope you know how to multiply a matrix by a vector. So you are just putting here 1 to 1, and then you multiply. -1. Can you multiply that one? What is the first variable of this vector?
Two.
But you should be quick, because this multiplied by this, everything is 0. So this is 2. Here multiplied by this is what? 1 plus 2 plus 2. That's 5. And then this multiplied by this is 1 minus 2 plus 4. That is 3, right? No. Yeah, that's 3. So you should be, at least you should be even multiplying. And then, as I said, that we normalize by this quantity. So I'll put 3 outside, right? And I have what? If you have these values, you can divide by 3. Divide this by 3.
2 by 3.
But so use, let me just for now keep fractions, but next time use what? Use fractions, right?
Okay,
And then this is 1. Yeah. And so this, what you get here becomes your x1, and what you put here becomes what? This is the first eigenvalue. So it means after one iteration, your eigenvalue is 3, your eigenvector is this one. And then next now you have A multiplied by AX1. What do I get? Multiply this now A by this vector. And so this now, when you have the calculator, you know you have just only changed this quantity to this. If you multiply, what do you get? I made a mistake, right? Somebody wanted, let me change this. So the mistake I made is somebody wanted us to normalize what? X1, right? So let me just keep that one. So by normalizing X1, what does it mean? It means I'm taking out 2. And then I have this is 1, this is 2.5, this is 1.5. But as I told you, you can also still normalize the third one, still looks okay. Now next, so this becomes your x1. So now can you put this quantity here and then you multiply quickly, and then you tell us. I think you will do this maybe. You will do it later on at home. Because this is just now doing the same thing. Now, can you just a second example, and then you can again try. So can you record what's our J? Can you record our J? What's our J? The one from the other method. Zero. Negative 6/15. This was also negative 1/4, right? This was 0. This is 0. 27. 1/27. Negative 2/15. If you want, you can put those in the decimal place. So we said we want to find the dominant eigenvalue of this matrix to check if it's less than 1 or not. So to find the dominant eigenvalue, I just told you need to make an initial guess of an eigenvector, right? And you start making this simple. Just decide which one do you want to normalize, the first, the second, or the third component. But this one you should not even think, because I told you each one can give. Just I want you to decide. So you should not even start thinking that which one works. So somebody has said 1. So since I want to normalize this, I can put 1, and then I can just make this 0, just to be simple. So when you learn some of these things that you are trying to with initial guess and you want to multiply, try to find things which are easier to multiply. And then when you multiply now, what is J x naught? What do you get? Multiply J by x naught. One over 27. Negative 2/15. Then the third one is, now we are screwed. This one will screw us because one of the eigenvalues is 0. So this one we cannot. So this method here we cannot be. No, first, what is the determinant of this matrix? I think if this determinant is equal to this, might or might not work. So if this if we have 0, we cannot divide by 0, basically. So we can try to make this as one of these non-zero, so that we don't end up messing. We don't. So I can just decide to make this 1. I'm just trying to. So because if you have 0, you cannot divide it by 0, and so that's why I've just changed this one so that we don't get a 0 vector. And whichever matrix I give you, this method does not work if you have some repeated dominant. We assume that eigenvalue is 1. If you have repeated, you may have problems. So if I give you an example somewhere in an exam, I'll be sure that it works. So I'll be sure it works. If the example requires so many steps, I'll make sure that I start somewhere where somebody requires at most 5 steps to converge. That's enough for an exam. Because once you illustrate this, then you can quickly get this thing done, and then you move forward. I don't know if I can try to do it just roughly on the calculator. No, on the calculator. On what? Maybe on the laptop. I don't know. Maybe I should try on the laptop. Maybe. Do you want me to illustrate? But I think you should be at 23. Do you want me to do it to illustrate here? But why? So let me share this other screen. But so those things you have to go and do them. Make sure that you try. They are forming part of the assignment. So I said the assignment 2, you are having the SOR method, just write down the formula. And once you write down the formula, then you will, let me first share a window and share. You now program that method. And then after you program it, you also now do the same for these other methods. Just now compute the matrix, the iteration matrix, and then compute their dominant eigenvalues. So maybe, I think I heard somewhere, I wrote somewhere simple examples. I can just start with a 2x2 example. So do you see my screen? And I just don't want to program. I just want to do what I told you. So I am putting the matrix A, right? And then if we want, we can now make the program. So the matrix A is -2, then -3. And then the second row is 6, 7. So that's the matrix. First of all, just to see the eigenvalues, like I can just put here, MATLAB has the eigenvalues. So the eigenvalues are 1, 4. Those are the eigenvalues of this matrix. So you can, by the way, here you can easily get the eigenvalues just by finding the eigenvalue. But since we are learning that method, power method, we want to try to see if we can get something close to 4. And so having that matrix, let me first remove this, and then I can put this back here. So having this matrix, can somebody guess for us the vector we start with? Like even x. So we start with, okay, I need a vector, right? I start with 1, 2. So basically when you start with this, it just means what? That we are normalizing the first quantity, right? Is what you kept as 1, right? No, I think if I do this, then it will disturb. Let me put as a column matrix here. That 1, 1, 2. Because you normalize the quantity you set as 1. So once you generate the new vector, you just have to divide by that value, so that you make this control as 1. And so I told you we form the new matrix. Let me call it V as is the product of A multiplied by now X. So you just now, I'm not calling X1, but you call it X1. Then I get -8, 20, right? And so -8, 20, what happens here is you now want to normalize the first quantity. So it means the eigenvalue 1 is this quantity -8, and then I divide by this quantity. So I can say that x is the same as V divided by V into 1. So I'm dividing by the 1. I'm just displaying this one so that you see them. Then I get what? -1. It's 1 and then -2.5. So that's our new x. And since MATLAB remembers, because I'm updating, I just take again A multiplied by X, this line. And then I get the new V. So the new V is -5, 5. That means that's the second approximation of the eigenvalue. And then I can divide by that quantity again. That's what we have been doing there. So I divide by that quantity again. So since it's here, I just divide by the same quantity. And then I get 1 and then -2.0. With my new approximate eigenvalue is 5.5. I started from 1 eigenvalue, I go to -8, I've now gone to 5.5. And then I keep going again. Once I get x, again I multiply by A. I get -4.27427. So that means my new approximation of the eigenvalue is 4.27. But again, I normalize, I get x, and I multiply again A. I get 4.06. So are you seeing where are we heading to? Because so whichever quantity you get at the value you are normalizing, that's the eigenvalue. Because you are dividing by it, so it means it's coming outside. So the new eigenvalue here is 4.0638. And so I divide again, I get the new eigenvector. So this is the eigenvector now, if it's correct. And the eigenvalue will be this. And then I multiply by the matrix, I get another value. The new eigenvalue is what? 4.0157. So do you see that it's going to 4, right? Depending on the initial value you start with, this method can take long. It's just the iteration matrix. So it's also, as we said, when you start close to the eigenvector, then it will quickly converge. Maybe you need 3 or 4 iterations. Otherwise, you keep on going. And so once you do this, I divide again, and then I multiply by the matrix, and then I get 4.0039. And then I divide again and multiply by the matrix. I get 4.0010. So you see that we are turning to the solution. And then I divide again, and then I multiply by this, 4.002. So assuming if I stop here, 4.002 is eigenvalue. Eigenvector will be what? Will be 1 and then -2. If I multiply this, then I get 4.001. Then the eigenvector is 1 negative. So it means we have converged already. So you see I've gotten already 4.00. So that's the eigenvalue. So you keep on the value you are normalizing as that fixed value as 1. So that's the process I've just been doing. And then you can easily, so if you have one program here, you can easily program. Just get a matrix A, and then you keep updating, and then you create a loop. Right? Any question? I hope you have been seeing my MATLAB screen because I was sharing 2 screens. Okay. So I just decided to do this on the command window. I didn't program this, but I've been seeing it on the command window. Is there a question? If no question, then we can stop there. Yeah. So the assignment already. So the assignment involves, maybe let me just type here. So the assignment involves putting SOR method, right? So just here, what you need is what? Just the formula, and then an example, then program it. So you just have a formula, you have an example. Of course, you have to do it by hand because you have to understand by hand. And then you make a program to do the same formula. Then to implement Jacobi and Gauss-Seidel methods. Find their corresponding matrices and dominant eigenvalues. And then the last one is what? I think these are in fact they are just these are the assignments. So because something lies here, so even I know you can get eigenvalues by just using the eg command in MATLAB. It gives you the eigenvalues, but I want you to try to implement this technique of the power method so that you get the dominant eigenvalue. So find the dominant eigenvalues. Let me put here maybe using the power method. Let me copy this and maybe send it to what? So I've sent it to chat. So those are those are the assignments too. Yeah. So for those who have not presented, I think I'm not tired, but I have.
Yeah. So group 9 is ready.
Yeah.
Group 9 is ready.
No, I think I need to reserve some of the things here. I'm supposed to go somewhere for a conference, and I've not booked the hotel, so I need to try to book the hotel before midnight.
Okay.
So those who have not presented, you can plan to
Yeah,
present.
excuse me.
Mhm.
Yeah, I wish to follow up on the class text. I'm not aware if you shared with the rep.
Which one?
You are supposed to share to us a textbook that you want us to use as the reference book.
Class rep hajawapati. I sent you 2 class reps. Kitambo sana.
Okay, I'll
Sijui
follow up.
class 12 wasema.
You shared with us. You haven't shared with the class.
Eh?
If you share the material, we must have forwarded to the class. So
So will forward.
maybe you got the kama ulituma nilituma.
No, I thought because I sent you some textbook, right?
Yes, we received the book.
Yeah. So huyo mwenye hajapata mtumie.
Okay, thanks.
Atafute.
Hao watu wenye haja present saizi.
Yeah.
Oh, at least me no now. I have to do those things. So you can try to find me on Friday evening. Your Friday. No, what do I say? I think my Friday. I don't know if I have activities on Friday morning, but you can try to check with me on Friday morning. If not, if period is night, is it Saturday? Let me first check.